Tested in one environment at a time, this component withstood temperatures of 1600 degrees Fahrenheit and vibrations of 5 to 2,000 cycles per second at 10 Gs, or 10 times the force of gravity. Pronounced safe by today's established methods of single environment testing, this instrument might have been used in one of today's space systems, only to fail in outer space under the multi-stress conditions of space vehicle environments. Information available concerning the tolerances of man and materials to single stresses of heat, altitude, noise, and single frequency vibration is well established. To random vibration, however, the information available is not advanced because it is based upon exposure to sine waves. That is, a single regular vibration or force pulse, repeating always with the same amplitude and frequency. In nature, and more specifically in manned space vehicle systems, vibrations are random, many irregular force pulses, whose amplitudes and frequencies vary continuously. In order to simulate spaceflight environments, test facilities and methods to produce and control heat, altitude, acoustical noise, and random vibration were devised by Boeing Environmental Test Laboratories. A master control tape with 5 separate channels is used to program the test. Electronic signals representing engineering data derived by the analysis of specific space vehicles and their flights are recorded on the tape by a multi-channel FM tape recorder. Each channel of the tape programs the environmental parameter for which it is responsible, causing the combined environments to vary in time and sequence. One tape channel programs the electronic temperature controller, which automatically turns on and off 3 4,500 watt heater units located in the base of the vibrating chamber. A thermocouple in the chamber is the feedback for the controller, which is monitored by a technician to assure the correct temperature curve. A second channel programs an electromagnetic vibrator with a frequency range of 5 to 2,000 cycles per second. An accelerometer mounted on the specimen, in this case a space vehicle instrument rack, sends a signal to an analyzer which records the test data on an XY plotter. Another channel programs random acoustic noise by controlling a 200-watt amplifier which drives 4 loudspeakers in the dome of the environmental chamber. The compartment pressure can be programmed after the 1/2-inch plexiglass pressure dome is emplaced. The tape controls the X or horizontal axis of an XY plotter, and the pressure transducer inside the chamber controls the Y or vertical axis. A curve of pressure versus time, representing the compartment pressure profile, is predetermined by engineering analysis and placed on the blotter before the test. Pressure valves are then opened and closed by a technician to trace out the curve for the right air pressure or simulated altitude profile within the chamber. After the environments on the tape have been checked for accuracy and synchronization in relation to each other, a 5th signal, the binary timing code, is placed on the tape. The binary signal allows any portion of the tape to be located at any time for test evaluation. One by one, the different hydraulic fittings, electrical instruments, meters, generators, motors, and other critical parts of the space vehicle system are subjected to their respective stress environments and evaluated. But no single part of the system is as complicated and complex as the human body with its multiple resonances. Identifying physiological tolerance problems related to space systems not yet existing is extremely difficult. The complexity and expense of analyzing and solving these problems is immense. But because research is a time-consuming process, we can't wait until a specific space system is completed before beginning to test and train its crew. Like the materials in the system, the man must be tested under the environmental stress combinations he will experience during flight. During the test, a restraint harness holds the subject's torso so he can move his head, arms, and legs without changing his relative position. Accelerometers at head, shoulder, chest, and hip levels sense and record human body transmissibility and roll-off characteristics under vibration. For pilot safety, the flight control handle is fitted with a switch that stops the test when the pilot releases or loses his grip. The environmental chamber, enlarged for the man test by adding a stainless steel cylindrical section and an aluminum conic structure, was proven safe at 1/2 atmospheric pressure by sealing and submerging the upper sections in water to a depth sufficient to produce 2 atmospheres of pressure differential. All other equipment is the same as that used for structures testing, except for instrumentation added to sense and record the physiological reactions of the pilot. During the test engineer is in contact with the pilot and maintains a constant surveillance of the test parameters.
All right, we're ready to go.
This will be a simulated launch, orbit, and re-entry. There will be 2.2 minutes of vibration during launch. Your cabin pressure will climb to 18,000 feet and hold. We will be in orbit for 15 minutes, during which there will be no vibration. Re-entry will take 6.6 minutes. The maximum vibration intensity will be 4.6 Gs RMS. Begin your tracking test on green light.
When all is ready, the master tape is started. The binary is counting off the final seconds before liftoff.
Okay, we have 10 seconds to lift off. Recorders on. Equipment on. Pilot. Pilot ready. 4, 3, 2, 1, 0. Liftoff.
As the simulated spacecraft lifts off the pad, the large 25,000-pound force vibrator reproduces 2 independent random vibration curves simultaneously. The low frequencies range between 2 and 20 cycles per second, and the high frequencies between 20 and 2,000 cycles. The intensity of each vibration varies as it would during the actual flight. The cabin pressure drops from a normal 14.7 pounds per square inch to 7.35 as the spacecraft gains orbital altitude.
We have 6 seconds to first stage separation. 3, 2, 1. First stage burnout.
Roger. Separation okay. Second stage ignition okay. Cabin pressure is 735 and holding steady. Cabin temperature 120 degrees.
We will now begin numbers reading. Read banks 1, 2, and 3.
9380, 3384, 27738.
Lapse time readings.
103.
Begin tracking with next green light. 6 seconds to second stage burnout. 3, 2, 1, 0.
Roger. Separation okay. Third stage ignition okay.
After injection and third stage burnout in orbit, there is no vibration until the space vehicle is buffeted by the atmosphere during re-entry. Random vibration during re-entry is less severe than during boost. During boost, the vibration pattern is broken into sections by staging, while during re-entry, random vibration reaches its peak when the vehicle first contacts the atmosphere. Body temperatures remain normal throughout a cabin temperature fluctuation of from 80 to 120 degrees Fahrenheit. The higher temperatures occurred during boost and during re-entry when the skin of the spacecraft reaches near 3,000 degrees Fahrenheit. Electrocardiogram, body temperature, respiration, rate and pattern recordings, urinalysis before and after each flight, and examination of eye grounds for blood vessel damage showed no effect on the pilot. Although respiration and pulse increased slightly during boost and re-entry, none of the subjects exposed to the maximum random vibration and environmental envelope experienced irreversible physiological damage. In this Boeing facility, by gradually increasing a conservative beginning, man has experienced and found tolerable the combined environmental stresses of heat, altitude, random noise, and random vibration at intensities exceeding those inherent in today's hypersonic spaceflight vehicles. In the final analysis, man himself must evaluate his own performance capabilities by experiencing environmental stress combinations as they occur during actual space flight. Today's testing of tomorrow's spacecraft systems provides more effective data for design engineers and assures the success of our space programs. Inadequate testing would jeopardize the man, the mission, and our future in space.